Hi there, my name is June and welcome to another video of Learning with Levi. In this video, we'll be comparing SN1 and SN2 reactions and doing some example problems. We've started doing podcast format for those who'd like to reinforce these concepts on the go, and any mechanistic stuff will solely be in the video. So I'll link the podcast down below, and for those just listening, I highly encourage all of you to check out the YouTube video for the visual aspect as well as the example problems. I'll put a timestamp down below if you want to skip the comparison part and go straight to the examples. As always, let's define a few things. A nucleophile is a species that donates a pair of electrons. An electrophile is a species that accepts a pair of electrons. A leaving group is an atom or molecule that leaves another molecule during a reaction. And lastly, a substrate is a compound being attacked by the nucleophile. Alright, so let's compare SN1 and SN2 reactions. So SN1 reactions are unimolecular reactions, while SN2 reactions are bimolecular reactions. When we say that SN1 reactions are unimolecular, it means that the rate of the reaction is dependent only on the substrate. When we say that SN2 reactions are bimolecular, that means that the rate of the reaction is dependent on two reactants. Now, SN1 is a two-part reaction, while SN2 is a concerted reaction. SN1's first step is the formation of a carbocation through the loss of a leaving group. Step 2 of an SN1 reaction is the nucleophile attacks that carbocation and forms the product. With SN2, we say that the concerted reaction, that means that the bonds break at the same time that the bonds are broken. So in this situation, the bond formation between the nucleophile and the electrophilic carbon is being formed at the same time as the breaking of the bond between the electrophilic carbon and the leaving group. Now, the third point is that SN1 reactions do not need strong nucleophiles to proceed, while a strong nucleophile is needed for an SN2 reaction. With SN1 reactions, the strength of the nucleophile is not as important because the nucleophile is not part of the rate limiting step, again, which is the carbocation formation. Thus, weak nucleophiles will suffice in SN1 reactions. In SN2 reactions, negatively charged species is favored over neutral charge. For the period trends, as well as the period trends with the nucleophiles, the periodic trends, with the nucleophiles, with the rows, as you go left, it becomes more nucleophilic because the more electronegative atoms hold their electrons more tightly and thus are less likely to form bonds. For columns, it gets more nucleophilic as you go down due to the increased size and polarizability. The fourth difference between the SN1 and SN2 in terms of steric differences: for SN1, tertiary substrates are preferred over secondary, which is preferred over primary. This is because the rate limiting step is the loss of the leaving group and thus the formation of a carbocation, so we must stabilize that carbocation. And we do that with the help of alkyl groups through the inductive effect as well as hyperconjugation. So with that in mind, more alkyl groups help stabilize the carbocation better. For SN2 reactions, the opposite is true. Primary is preferred over secondary, which is preferred over tertiary. The nucleophile must be able to get to the substrate to attack it. However, as the substrate gets more crowded with alkyl groups, it gets more harder for the nucleophile to attack. We call that prevention of interaction steric hindrance. The primary substrate, which only has one alkyl group, will react with the nucleophile faster than a secondary substrate due to being less crowded, and so on and so on. The next one that we have are solvent differences. In SN1 reactions, polar protic solvents are favored because they help stabilize the carbocation through hydrogen bonding. SN2 reactions like polar aprotic solvents because the nucleophile isn't as heavily solvated as it would be with a protic solvent. Again, think of it like the concept of steric hindrance. Less hindrance, in this case less protic solvents, the more freely the nucleophile is able to react. Some examples of polar aprotic solvents are DMF, acetone, DMSO, and DME. The sixth difference is the leaving group in SN1 and SN2. In this particular case, both reactions do favor good leaving groups. Weak bases want to accept electrons and thus are good leaving groups. And now we have weak bases that are also conjugate bases of strong acids. Again, for example, we have HCl, HBr, and HI. Their conjugate bases are really great leaving groups, Cl-, Br-, and I- respectively. Other leaving groups that are great are sulfonates, sulfates, and phosphates because of resonance structures, and due to the resonance structures, they're able to help stabilize the molecule. The next difference is the stereochemistry difference between SN1 and SN2. SN1 reactions will get a mixture of retention and inversion. With SN1 reactions, the carbocation is sp2 hybridized and planar. So that means that the nucleophile can attack the carbocation from the top or the bottom. Allowing that will give two enantiomers of the product, which we call racemization. SN2 reactions produce inverted products only. And the reason why that is because the nucleophile attacks on the opposite side of the leaving group, which we call the backside attack. And when this happens, the inversion of the configuration happens at the carbon that it occurs at. The last comparison is rearrangement between SN1 and SN2. With SN1 reactions, the first step is the carbocation formation. Again, the carbocation wants to rearrange to help form more stable carbocations, and the hydride/methyl shifts can rearrange with its bonding electrons to form more stable carbocations. With SN2 reactions, because there's no carbocation forms, hydride and methyl shifts, aka rearrangements, do not occur. Alright, so now that we have that all compared, let's do some examples. So with this example, let's try and figure out which one of these will be a better SN2 reaction. So in the first example on the left, we see that it looks like we have a primary substrate because the bromine is only attached to one carbon. On the right, it looks like we have a secondary substrate because the bromine is attached to two carbons. Now, if we look at this flashcard on the right, SN2 reactions prefer primary substrates right here over secondary. So the compound on the left will be better for SN2 reactions. In the second example right here, we can see that both compounds are primary substrates. The only difference is the leaving group. And so one is a bromine and one is an iodine. And between the two, iodine is bigger and more polarizable than bromine because because iodine is more polarizable, it's a better leaving group, making it a better substrate. So we would choose this one as a better substrate for SN2 reactions. All right, and the next example is right here. And this is an example of what is the end product going to look like. All right, so if we look at the study aid on the right, this is what a general SN2 reaction looks like. The nucleophile and its lone pairs attack the electrophilic carbon from the backside and form a bond, while the bond between the electrophilic carbon and the leaving group break. Again, we call this whole interaction, or this whole step, a concerted reaction. The leaving group leaves then with its bonding pairs of electrons, and then we form the ether. So as you can see mechanistically right here, again, the nucleophile attacks with its lone pair on the backside of the leaving group, and then the leaving group then leaves with these bonding pairs onto the leaving group. And this is the product right here, and this is an ether. And to make sure that we have the right product, we always want to count the number of carbons and make sure that they match. So as you can see right here, we have 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons, and so our product should have a total of 8 carbons. So if we count them, that's 1, 2, 3, 4, 5, 6, 7, 8. All right. The next example is a proposed mechanism of how this right here turns into this product. So in this example, we want to look at the flashcard right here saying that water is a good leaving group. And I guess the question now is, how do we get water as a good leaving group? Now, if you remember from the previous videos, we mentioned that the alcohols, under certain conditions, i.e. acidic conditions, the alcohol will be protonated and thus make it a good leaving group. All right, so if we move our screen to the right, we do have an alcohol in a acidic solution. In this particular case, it's a sulfuric acid, H2SO4. So the alcohol gets protonated, as you can see right here, and thus we have everything for an SN2 reaction to occur. So we can see we have a good leaving group, which is this right here. We have a primary substrate, which is this right here. And then we have a strong nucleophile. In this case, it is the hydroxide. And so what you can see is that the nucleophile, with its lone pair right here, it attacks the backside of the leaving group, in this case the positively charged water. The leaving group leaves, and then we form a cyclic ether right here. As always, we want to make sure that we count the number of carbons, make sure that we don't lose or add any carbons. And so in the beginning we have 1, 2, 3, 4 carbons, and then at the end product we have 1, 2, 3, 4. All right, now let's move on to some SN1 reactions. All right, in this example, we want to make sure that we distinguish between which one would be a better SN1 reaction. So in the first example, we have a secondary substrate versus a tertiary substrate right here. Again, if we look at the flashcard study aid on the right, we see that the tertiary substrates are more favored over a secondary substrate because the alkyl groups are helping stabilize the carbocation when it forms. So the compound on the right here will be a faster SN1 reaction. In the second example, we have a secondary substrate. As you can see right here, this is bonded to 2 carbons versus this one right here on the right is only bonded to 1. So again, we have a secondary substrate over a primary substrate, so the compound on the left will undergo an SN1 reaction faster. Last example that we both have secondary substrates. As you can see right here, they're both bonded to 2 carbons, 1, 2, as well as this one, 1, 2. Now, the only difference is the double bond. Now, as we mentioned earlier, alkyl groups help stabilize carbocations. There is another way to help stabilize the carbocation, and it's through resonance structures. Now, with resonance structures, we're able to spread the positive charge over 2 atoms. Now, if we go to the right, we can see right here that with the resonance structures, the positive charge is spread over 2 atoms. So this one right here, as well as the other carbon right here. And then this will help undergo the SN1 reaction faster because it's more stabilized. All right, and then the last example, we're going to help differentiate between SN1 and SN2 reactions. All right, in the first example, we have a tertiary substrate and a weak nucleophile. Now, if we look at the flashcard study aid on the right, we can see that tertiary substrate and a weak nucleophile favors an SN1 reaction. So weak nucleophile right here favors SN1 reactions. Tertiary substrate favors an SN1 reaction. Now let's see how this works mechanistically as an SN1 reaction. So we can see right here, we know the first step is the formation of a carbocation. The bonding electron between the carbon and the leaving group leave with the leaving group indicated by the small red arrow, as you can see right here. The bonding electrons leave. Then we have a tertiary carbocation ready to be attacked by the weak nucleophile, as you can see right here. In this case, the weak nucleophile is the water. So then the lone pairs of the nucleophile attack the carbocation, and we get this product right here. Now the iodide that that was the leaving group before deprotonates the water, and thus we form this product right here in the orange box. All right, and now if we go back to the first example, we can see this last example right here. We have a primary substrate as well as it is all in DMSO. Now again, if we look at this flashcard right here, the study aid, we see that the primary substrate as well as aprotic solvents favor SN2 reactions. So primary substrate right here, as well as DMSO, which is a polar protic solvent which favors SN2. Again, let's move it to the right so we can see mechanistically how this works out. The iodide atom attacks on the backside of the electrophilic carbon, as you can see right here, and at the same time the leaving group leaves, and this forms the product right here on the right in the orange box. All right, well, this concludes the comparison of SN1 and SN2 reactions. Hit that like button, subscribe button, support the channel, and share it with your friends who need help with organic chemistry. The next video we'll be going over elimination reactions, and so I'll be putting out more videos, so comment down below what you'd like to see. Social media links will be down below, and as always, remember, you gotta go.